So in this class, we will discuss a problem of plotting bending stress and shear stress diagrams for a beam which is having a T section. So this is an examination problem. So it runs like this: a T section of flange 120 mm by 12 mm and overall depth 200 mm with 12 mm bend thickness is loaded such that at a section it has a bending moment of 20 kN/meter and shear force of 120 kN. Sketch the bending and shear stress distribution, marking the salient values. Now we will write the section first. So it's a T section. So with the flange 120 mm width by 12 mm thickness and web overall depth is 120. So overall depth is 12 is here. So remaining web depth will become now 188 mm. Total should be 200. And the thickness of it is 12 mm. And at a section in the beam, we have given bending moment value as 20 kN/meter and shear force value F as 120 kN. So at this particular section, we have to plot the bending stress and the shear stress distribution diagram. So in the last class, I have given how the bending stress and shear stress patterns will be there for a T section. So here let us plot that for this problem. First step is to locate the centroid. So location of centroid, that is the first step, because once you locate the centroid, we can easily find out the moment of inertia, that is I value we need for both bending stress and shear stress computation. So let us plot that centroid. So because once you locate the centroid, through the centroid only neutral axis passes. So for locating centroid, I will take this as the x-axis, bottommost edge as the x-axis. You can see that the given T section is symmetrical about y-axis. Therefore, the centroid lies on the axis of symmetry. That means it lies on the y-axis. Suppose if you take this as the y-axis, definitely centroid lies on the y-axis. So by property of centroid always lies on the axis of symmetry. Now, if I take this as x-axis, the distance of the centroid from the x-axis is y bar. So we need to find this y bar. You know how to find the y bar value. So y bar is given by sigma ai by I divided by sigma ai. So this T section is divided into two rectangular sections. So this is one rectangular section, 120 by 12 mm. Another rectangle is 12 by 188. That is the red portion. So here sigma ai by I means a1 y1 plus a2 y2 divided by sigma ai is a1 plus a2. So here a1 is this area. Flange area I will take it as a1. Web area I will take it as a2. y1, y2 they are the distances of the CGs of those rectangles from the x-axis. So suppose if I take this as G1 and the centroid of this web portion as G2, these two rectangles, distance from x-axis to G1 is y1, distance from x-axis to G2 is y2. So we can write the values here. So A1 is area of this flange portion, 120 by 12. So it becomes 1440 millimeter square. A2 is area of the web, which is 188 by 12. So if you take the product, 188 into 12 will be 2256 millimeter square. So total area sigma ai becomes now the sum of these two, that is a1 plus a2, which is 3696 millimeter square. That becomes the denominator here. Then y1, distance of g1 from x-axis, which is 188 plus half of 12, that is 6. 188 plus 6, 188 plus half of 12, so it becomes 194 mm. y2 is distance of g2 from x-axis, which is half of 188. So 188 divided by 2, which is 94. So these are the values. Once you substitute these values, substituting, we can get the value of y bar. Y bar is the distance of the centroid of the T section from the x-axis, that is the bottommost edge. So y bar will be now a1 y1, that is 1440 multiplied by 194 plus a2 y2 2256 multiplied by 94 divided by a1 plus a2 3696. So if you simplify this, you will get y bar in millimeters. So that is the distance of centroid from the x-axis under consideration. So 1440 multiplied by 194 plus 2256 multiplied by 94 divided by 3696, which is 132.96 mm. That is the y bar value. Once again I will check. 1440 multiplied by 194 plus 2256 into 94 divided by 3696, so 132.96 mm. So this is the distance of centroid from the x-axis. Now once you go against this distance, now we can find out moment of inertia also. So in mechanics we have learned how to find the moment of inertia using parallax theorem. So I is nothing but now I and A, because the neutral axis coincides or passes through the centroid. I is nothing but I and A. So by using parallel axis theorem, we need to find this. So these two steps are important: location of centroid and I value, finding I value. So here, what I will do here is, once again for finding moment of inertia, we need to use the two rectangles separately. So according to parallax theorem, first I will write the moment of inertia of the top rectangle, this one, that is A1, BD cube by 12 for this. So please note that. So here we need these distances for calculating moment of inertia. So let only I will take only those distances. This is G1, G is here, G2 will be here. So you know the distances now. From here to here, this is y bar. We got it as 132.96 mm. Okay. G2, this distance half of 188, that is 94. And this distance y1 value we got 194. And these three distances I need. Now from this you can calculate the distance between G and G1. Distance between G and G1, this value. So this value will be, suppose if this is 32.96, let us calculate this value. Total is 200. 200 minus 132.96. 200 minus 132.96, which is 67.04. So from this 67.04, you have to deduct this. This is 12 mm. So you have to deduct 6 mm. So that becomes this value. That means it becomes 61.04. Distance from G to G1 is 61.04. Next, distance from G to G2, these two distances we need. It is 132.96 minus 94. 132.96 minus 94, which is 38.96. 38.96 mm. So these two distances, that means distance from G to G1 and distance from G to G2 is required for computing the moment of inertia. Now I will write the moment of inertia of this top rectangle, with respect to the neutral axis. So using parallax theorem, that is BD cube by 12. So BD cube by 12 for that first rectangle is B is 120, D is 12, BD cube by 12 plus area A1. So area A1 is 120 into 12. Area of that is 120 into 12 into distance square. Distance square means this distance from G to G1. Square of that, that is 61.04 square. Yes, this is the moment of inertia of the flank portion about the neutral axis. Plus, I have to add the moment of inertia of the web portion now. Same procedure is used. BD cube by 12 for the web is B is 12 for the web. D becomes 188 cube by 12 plus area of web portion, that is 188 into 12 or 12 into 188 into distance between G and G2, 38.96 square of that. Yes, if you add these two, you are going to get the INA value. The first part is for the flank portion, second part is for the web portion. Now let me calculate this. You will be very careful in calculation. So 120 into 12 cube by 12 means some square. So 120 into 144 can take plus 120 into 12 into 61.04 square. So the first value is, I can write 5382 549.5. This is the first value plus second value, this one, 12 into 188 cube. So 12 into 188 cube divided by 12 only plus 188 into 12 into 38.96 square. So it becomes 10069 012.9. Yeah, this is this value. So please check the values. So once you add these two, you are going to get the I value or IMA value. Let me add these two plus 53,825 49.5. So it comes out to be 1545 1562.4. Yeah, this is the value of I. It will be in millimeter power 4. So these two steps are very important. First locate the centroid by finding y bar, then find out the moment of inertia. Now, once you get these two values, now it will be easy to find out the stress values. So first I will take the bending stress values. So you know that bending stress diagram is a linear diagram. Only two values we need to find. One value at this top fiber, another value at the bottommost fiber. So here G is here. We have located already neutral axis. So bending stress diagram will be like this. We need only two values. So this stress diagram will be like this. This is the stress diagram. This is a straight line. So suppose if it is a simply supported beam, above the neutral axis it is compression, below the neutral axis tension. If it is cantilever beam, above the neutral axis it is tension, below the neutral axis compression. Anyway, he has not given anything about that. So let us find out the values here. This side it has F at the top, F at the bottom. These two values we need. So these values will be in Newton per meter square. So the bending stress value here, F value will be 0 at the neutral axis. That's why I have shown here. So now across the section, let us find out only two values we need now. F top and F bottom. So the governing equation is M by I is equal to F by U. This is the pure bending equation which is used to find the bending stress. Now I need F value here, so F will be M by I into 1. Now let us convert all the values to newtons and millimeters. So using this equation we can find out F top and F bottom. So what I will do here is, now F top will be Ft. M is 20 kilonewton meter, he has given at that section. So kilonewton meter should be converted to newton millimeter. So 20 into 10 power 6 divided by I value is this 154 51 562. 154 515 62.4. This is I value multiplied by y becomes here this distance. Please note that this is y, or you can take it as yt. So yt value is here, you can see this is above the neutral axis, this is the T means it is top. So we have to take this above the neutral axis, that is this value is 67.04. So 67.04. Now if you simplify this, you will get F top. So that is the stress value here. So 20 into 10 power 6 divided by 154 515 62.4 into 67.04. So it is 86.77 Newton per mm square or MPa. So this is the bending stress at the top fiber, 86.77 MPa or Newton per mm square. Similarly, you can find out F bottom by just writing y value as this value 132.96. Only this will change, this will not change. That means here I will write here F bottom. Stress at the bottommost fiber is same M by I 20 into 10 power 6 divided by 154 515 62.4 multiplied by y value is 132.96. So if you simplify this, let us check what we are going to get. 20 into 10 power 6 divided by 154 515 62.4. This multiplied by 132.96, 172.1 Newton per mm square or MPa. So this is the stress at the bottommost fiber. So the value is 172.1 MPa. So this is about bending stress. So this is linear. Bending stress diagram is always a linear diagram because you can see here F is directly proportional to M is a constant, so it is directly proportional to y. It's not directly proportional to y square. It is y. That means it is along the depth. It is linear relation. So these two are the values. Now we can plot the shear stress diagram also for the same section. So we got 86.77 MPa on the top and 172.1 MPa at the bottom with y bar value as 132.96 mm and I value as 154 515 62.4 millimeter power 4. Now let us plot the shear stress diagram, then the problem will be completed. So to plot the shear stress diagram, I have shown you how the shear stress variation will be there in the case of a T section. How many values you need to find, that also I had explained in the last lecture. So you can see here. So I will now try to plot the shear stress diagram. In the case of T section, the shear stress distribution So now shear stress distribution. So this is the given T section. Let us have the values here. G is here, total axis. So this distance, you know that it is 132.96 mm. 132.96 mm. This is 120, all are in millimeters. This is 12. This is 12. Okay, so these are the things. Now we have to plot the shear stress distribution for this. The shear stress will be having distribution. So here and here Q will be 0. Please note it is 0 here, 0 here. At the bottom of the flank and at the top of the well, we will be having two values of shear stress. Q BF will be there. Then at the same level we have Q TW. BF means bottom of flank, TW means top of flank. So then at neutral axis level we have maximum value Qmax. Now we have to join all these by parabola. Variation is a parabola, straight line, at the same level it is straight line, then parabola once again, then parabola once again. Please note that this is parabola. Now our aim is to find these values. All the values will be in Newton per mm square. This is shear stress distribution. Now let us how many values you need now? Here it is 0, here it is 0. QBF, QTW, Qmax. So those three values you require for plotting the shear stress diagram. Now one by one we will calculate. We will write. Let me write the formula first. So shear stress is given by Q is equal to F into AY bar divided by I into B. So this is the standard formula. We need three values. First I calculate QBF. QBF. So QBF means shear stress at the bottom of flank. When I calculate QBF, B we have to take flank base, that is 120 mm. 120 mm. Now the value of F he has given at this section as 120 kN. Convert it to Newton. 120 into 10 power 3. That is the F value. Into AY bar we have to calculate. Please note that AY bar means whatever area is there above that layer. So I am considering the layer here now. This is where I am calculating the shear stress now. Above that, whatever area is there, that area. Into Y bar is the, you have to locate the centroid of that area. It's a rectangle. Distance from that centroid to this neutral axis is your Y bar. So A will be now here 120 into 12. Please note that area is 120 into 12 into Y bar is distance from here to here. Here to here. So that is, you can see here. So this distance is 200 minus this. 200 minus that means it is 67.04. 67.04. So from this I have to deduct half of 12 because I need this distance, that is 6 I have to deduct. So it will be 61.04. So this is AY bar. So be very careful in calculating this. Divided by I value, you know, it is 154,515. We have calculated that. 154,515, 62.4 into B is 120. So this is, you have to simplify this. This will give the value of QBF. Now let us calculate this. 120 into 10 cube into 120 into 12 into 61.04. So that is the numerator, divided by 154,515, 62.4 divided by 120. So it comes to 5.69688 or 69. 5.69 Newton per mm square. You can just see the values of bending stress and shear stress. Bending stress will be more the shear stress will be less. This is one value. Next, second value I need is QTW. QTW is the shear stress at the top of web. So that means at the same level, but B we have to take width of web, that is 12 mm. B will be 12 mm. This is the difference. So for this, so these terms, so numerator is same, I is also same, denominator only instead of this 120 we have to take B as 12. So now if you simplify on the same line, 120 into 10 cube into 120 into 12 into 61.04, this remains same, divided by I is also same, 154, 515, 62.4, only this is instead of 120 it is 12. So you can see that when it is divided by 120 you are getting this, when you are divided by 12 it is 10 times more than this, that means you are going to get the value as 56.9. 56.9 Newton per meter square. This is shear stress value will change. Now that means this value is, we got 5.69 MPa. This value I got 56.9 MPa. Now the third value Qmax I need. So Qmax, to find Qmax what you have to do here is at the neutral axis level. So Qmax is equal to QNA. Same formula. So, but here A into Y bar will change. So, neutral axis is here. Here at this level B value is 12 only because the neutral axis lies in the web bar. So, B value is width of web only. So, B we have to take 12 here. B we have to take 12 mm. But A into Y bar is important here. So, what is A into Y bar? Now, here either you can take above the neutral axis or below the neutral axis, whichever is easier for you. Now, if you consider below the neutral axis, so this area, it is a rectangle, it is easy. If you take above the neutral axis, you can say T section, you have to locate the centroid of that T section and you have to take the distance as Y bar. Better you take below the neutral axis, it is a rectangle. So, for this rectangle, so please note, for this rectangle, shaded rectangle, you locate the centroid somewhere here. So, this distance becomes your Y bar now. Now let us calculate the area first. So here F is same, 120 into 10 cube into A is area of this rectangle, it is 12 into 132.96, 12 into 132.96 into Y bar is the distance of centroid of this, that is here to this point to this neutral axis, which is half of 132.96, half of 132.96. So this is A into Y bar divided by I remains same. I is 154, 515, 62.4 into B is 12. So this is the value of Qmax. Let us see how much we are going to get. Newton per meter square. Let me simplify that. 120 into 10 cube into 12 into 132.96 into, see half of this will be 66.48 divided by 154, 515, 62.4 divided by 12. So you are getting 68.65. 68.65 Newton per meter square. So this Q maximum will be 68.65 Newton per meter square. So this is the shear stress diagram. You can just show arrows. So this is shear stress diagram. So for the T section, now we got both bending stress and shear stress diagram. So this is how we have to do the first step is to locate the centroid, then find out the moment of inertia, then use the tube bending equation for plotting bending stress diagram, only two values you require, one at the top fiber and another at the bottom fiber. Then shear stress equation you use. Then you should be careful wherever depth changes. So depth changes at the bottom of flange and top of web. You will be having two values of shear stress, and maximum shear stress value always occurs at the neutral axis level. You can see the value is increasing here, 0 to 5.69, then 26.9, then 68.65. This is the highest value, maximum value. Then it goes to 0. That means somewhere here, the meaning of this is somewhere here. Suppose if you want the shear stress value here at this level, for example, this PQ. Here, if you want shear stress value, so this will be the shear stress value, QT. So like that, once you plot the shear stress diagram, so you can get the values of shear stresses at any required depth along the section. Similarly, bending stress also, once you draw the bending stress diagram, a linear diagram, then at any depth you can get the from the diagram, you can get the bending stress at the required level.